I've been staying in the university all time. The only time I got internship is with Micron, and then my PhD advisor talked me out of it because he wants me to become a faculty. Which now I think back, it's probably better to have some industry experiences. So I'm really glad to be here and talk to you guys, and because I feel like I start to see the different mindset between academia and industry and how things can work together. Okay, I'm going to talk a little bit on the most of the work I did during the postdoc time, and I tried to migrate some of these into my research here at the University of Minnesota. Since Chris already gave a nice introduction, so I'll just probably skip here. But basically, I start off by working on CMOS technologies, logic devices, and then the second half of my PhD, I just got a chance to work on quantum stuff, dilution fridge. So I pivoted more onto the condensed matter side. During the postdoc time, I was mostly working on magnetic topological insulators and unconventional superconductivity. So today, since I'm with you guys, I try to pick the most magnetic part of my research to present here. I've been here a little bit under 2 years now, so I gotta say I still haven't get enough of the snow. I'm still in the enjoying part stage of the winter weather here. Right now, my group, the big theme is we look at different materials, right, and different physics, and try to let's see, sorry, try to okay, incorporate different types of materials to two applications. One is we look at the classical CMOS and semiconductor technologies, and then we also look at applications in the quantum domain. So my lab capacities right now, we are mostly set up for material and device testing. We have a cryogenic systems goes down to 50-ish millikelvin, and we have all these room temperature setups, and we have some simple material preparation setups in the lab, and most of the work and devices are done at the Minnesota Nano Center, which have a nice clean room from a university standpoint. Okay, right. So I'm going to talk about a new type of well, not so new, but we're going to talk about magnetic topological insulators. And before that, since my background is a mix of the classical semiconductor, CMOS, and quantum, so I would like to draw an analogy between these two trajectories. So if you look at the semiconductor industry, right? So we start from the first transistor to first IC to the famous Intel's processor to today's VLSI. You can see from the very first step to a more matured product usually takes decades of the development, right? So this is even just one example. In some cases, it takes even longer to develop these technologies. So now we're looking at quantum computing era. A lot of people has doubts whether this will work, also there are a lot of hypes, right? So my take on this is eventually it will work. I don't see any major roadblocks to say this fundamentally will not work. I think eventually there will be a pathway. How long does it take? If we draw an analogy to the Moore's law or semiconductor industries, the first superconducting qubit is made in 1999. And then after 15 years or so, we start to see big companies investing in these and try to put some commercial looking products. IBM put together this full transmon qubit at that time was a sort of big deal. Today's Google, IBM, they can produce hundreds of qubits. We're sort of in a NISQ era, noise intermediate quantum era. So basically our qubit can do something. It's not very good, but at least it can solve some problems. So it's getting closer to earlier stage of the CPUs we have, right? If you ask what would this thing look like in another 2-3 decades, I don't know. So I would like to quote famous Richard Feynman's talk. There's plenty of room at the bottom. So there's of course a lot of ways we can prove this comparison. If you look at the early stage first transistors and first IC, they're actually not made with silicon. Okay, so they were actually made with germanium. At that time, the first piece of germanium was actually produced at Purdue. I was a proud boiler maker, and we all know that story very well. But you can see whatever technology we're working with on superconducting qubits, on quantum qubits, in 20 years, they might be looking completely different. So that's a lesson we learned from the semiconductor industry. So the key is the material innovation that will be a critical technology driver. Okay, so so what kind of material might have a space in the future for quantum applications? So we're looking at something that's dissipation-less, because most of the quantum happens at low temperature, right? We want to minimize the heat dissipation. It has to be fault tolerant. Today's qubits, we're looking at the fidelity of 3 nines, right? So which is pretty impressive considering the very first qubits was so shabby. Now we really make a big leap in today's technology, but 3 nines is nothing compared to what you guys are working on, right? So ideally, we want to develop some fault tolerant either hardware or software for these quantum applications. So also it has to be scalable. A lot of things that happening right now, it's very prototype. We use 2D materials, right? You know, the famous Scotch tape story, but those are not scalable, right? We're looking for wafer scale growth of these new quantum materials. Okay, so one example I would like to share is this 2D topological insulator. Basically, these are insulating inside, but if you think of 2D nature, then the edge would be conducting electron without any dissipation. These are topologically protected edge states, okay? These are like highways for electron or spin current. Basically, they are separated in terms of the traveling directions and also for the spin polarizations. So one analogy I would like to draw is like if you go to big city like LA or here in downtown, you always have these divided highways for traffic to go in and out. They don't use this two-way traffic, right? So same thing for the highway of these electrons. They're the same thing. Okay, so I would explain a little bit more about the materials, but that's the but before that, I just want to give you a little bit of refresher on probably a freshman physics or even high school physics on how Hall measurement is done, right? If you have a piece of semiconductor, okay, you sending currents through this channel directions, and then you can measure the Hall voltage and the longitudinal resistance, etc. Right? So Drude model tells us that if you measure the Hall conductivity, because of the Lorentz force, you will see a linear Hall resistance as a function of external magnetic field. Basically, you apply a field perpendicular to the current direction, you will see a Hall voltage, right? And the longitudinal resistance is basically field independent for first order, okay? Right, so what happens if you have a very thin layer of 2D material, well, not 2D material, thin layer of material, and it's extremely clean without all these scatterings? Now, when you do this measurement, you will see that the Hall resistance is no longer a line. It develops into these discrete plateaus or steps, right? And these are not some random steps, right? If you carefully measure the Hall resistance at each step, it gives you a number of h/e squared. And then there's some integer number as well. Okay, so this is a fundamental physical constant, right? It doesn't depend on the materials, doesn't depend on whether it's electrons or holes. It doesn't depend on the geometry of your sample. Okay, so h is constant, E is electron charge. So if you plug these in, you get quantum resistance, which is about 25.8 kilo ohms. So all these plateaus, if you carefully read the resistance value, they will be at integer fraction of the 25.8 kilo ohms. Okay, so that's amazing, right? What's more amazing is that if you look at the longitudinal resistance, whenever you get into these plateaus, the resistance of this semiconductor channel drops to 0. Okay, what does that mean? It means we are in a dissipation-less transport limit, right? So the current doesn't see any resistance. Okay, so it's almost like superconductor, right? Well, you don't have any resistance anymore. That's beautiful. All right, so indeed, this discovery made in the 1980s got Professor von Kliching from Max Planck Institute a Nobel Prize for this famous quantum Hall effects. Okay, so if you ask what happens here, see if this works. So basically, if you look at this 2D of electrons, if you study the density of states as a function of energy, right? For the 2D electron gas, we know that without any field, it's basically independent of the energy. Now, I have a nice animation here, but somehow it's not coming up. But what happens is when you apply a perpendicular field to this 2D electron gas, this energy level becomes discrete. Okay, these are called the Landau energy levels. If you solve this wave function of electron gas in the magnetic field, you will see that this discrete energy level, the energy gap in between, is proportional to the magnetic field. So each time a Landau level crosses your Fermi level, you create these nice steps. All right, so if you look at things at more classical point of view, that's probably easier to understand. So if you have these electrons, you apply a perpendicular magnetic field, all these electrons starts to do the cyclotron orbits, right? So they are inside this material, they are localized because magnetic force force them to spin around so they don't carry any current anymore, okay? So, but where this zero resistance come from? If the electron accidentally gets into the edge, okay, because now you have this magnetic field, these electrons would just keep bouncing against the wall and skipping forward. Okay, so you can imagine if the electron really gets into this edge, there's no way for it to turn back, right? So magnetic force always asks it to go this way. So that's how you can eliminate any backscattering. Okay, so that's why once the electron goes in there, the transmission rate is always 1. That's where this zero resistance come from. Okay, so this is a classical quantum Hall effect. You know, I personally enjoy doing this because I just really appreciate the beauty of quantization. You look at any samples, you always get this universal value of 25.8 kilo ohms. Right, so it's not easy to achieve. You gotta have a very clean samples, right? For 3-5 people, gallium arsenide, people can get tens of millions of mobility nowadays. You gotta do things at low temperature, but more importantly, you need a big magnet, right? So we're talking about a few Tesla at least, sometimes tens of Tesla. Okay, so in order to achieve that, this is an image from a mag lab in Tallahassee. This is, I think, one of their 35 Tesla magnetic field. These are still resistive magnets. So you can see how huge these things are, right? So if you want to make use of this dissipation-less states in quantum Hall, this probably won't work, right? You can't put this thing in your pocket, right? So can we find any states or systems that host these quantized Hall states without requiring any magnetic field. All right. That's what I'm going to talk about. These are called quantum anomalous Hall effect, and they can be achieved in these magnetic topological insulators. All right. So there's a little bit of fun history, twisted story on the trajectory on how we get here today. First, the first field-free version of quantum Hall effect was theoretically proposed in the late 80s by Duncan Haldane on this famous Duncan Haldane model. But he created this beautiful toy lattice where you have this sort of hexagonal graphene lattice, and you put a tiny magnet on each atom with a alternating field or magnetization. Then that will give you, overall, it will give you a quantum anomalous Hall effect with the net zero field. Okay, but you have to add sort of interparallel magnetism on each individual atoms. Right, so that's just a toy model. But in 2007, a group of physicists, experimentalists, who first demonstrate that if you have a 2D topological insulator, a mercury telluride, you can actually achieve these quantum spin Hall states. Okay, so if you look at their data, you can actually see it reached this quantum plateau at E²/h. You can see their data is quite noisy. There's a reason, because these states, yes, they do have this edge states, they do have this topological protections, but they have two copies of these edge states, one for spin up and one for spin down. And then they have this spin momentum locking, meaning that the upspin electrons going this way and then downspin electrons goes the other way. So if you have some defects on the edge that it introduces this spin flipping process, then the electrons can still turn back. So that's why this effect is not very robust. You can only see it when these two contacts are very close to each other, so the electrons can go through the other side without this spin scattering process. Okay, at least it's nice to achieve quantization without field, but still the quantization is not very robust. So what do? We lift the spin degeneracy. Okay, so we remove one of the spin channels. So the way to do that is, of course, we have to break time reversal symmetry, and the way to do that is to introduce magnetism. Okay, so the same group, they propose that what if we add some magnetic dopants into these topological insulators? Okay, so theoretically, they propose we can achieve a single channel without any magnetic field. Okay, so at that time, people tried this method, but it turns out all these spins in this system is mediated by the RKKY mechanism. But this is 2D topological insulators, so there are not a lot of itinerant electrons. So this idea turns out doesn't work. And in the 2010, people proposed another system. These are chromium-doped bismuth antimony tellurides. These are the magnetism is actually mediated by Van Vleck mechanisms. So even it's in topological insulator, we can still achieve magnetism. Okay, so I do want to point out that the time stamp here is 2010. The experimental realization, which I'm going to show next couple slides, is actually 3-4 years later. So to me, this is really remarkable, because most of the big discoveries in condensed matter physics, for instance, the superconductivity, quantum Hall effects, the experiments always predate the theory, right? So we accidentally found something and then we develop a theory to discover it. So this is one of the beautiful examples that theory guided the experimental discovery, because this is a very complicated materials, compounds, and the theories really help tell us what material you should use, what's the composition, and then we eventually will find that thing in their proposed system. Okay, so let me now explain how this works, right? So we know insulators, right? You just have a conduction band, valence band, you have a gap. Now you probably heard about topological insulators by now. It's still an insulator, right? But the conduction band and valence band are flipped. Okay, so you have inside these materials, the conduction band orbital actually is lower than the valence band. So if it goes out of the system to the vacuum, it has to come back, right? So in this case, at the surface of this material, you will have this Dirac surface states. So in other words, these surfaces are actually metallic. The bulk is insulating, the surface is metallic. Okay, of course, I draw it this way to highlight that metallic surface. It's not detached from the film. Okay, so it's still on the material, and of course there will be some side walls since this is a side walls for now. Okay, so in this case, bismuth antimony telluride is one of these topological insulators. Now we want to introduce the magnetism. We add some chromium. Chromium gives a perpendicular magnetic anisotropy to BST. So what happens is this magnetization introduces a Zeeman gap on the surface states. Okay, so this cracks open the Dirac surface states. Now you have an insulating bulk, you have an insulating surface. Basically, this thing is almost entirely insulating, except if you look at the edge of this surface states, you have a circulating current. We call it chiral edge states because you only have one spin going in one direction, because now you only have this one branch. And if you look at the group velocity of these edge states, it's all just one number, right? So that's why you only have the singular circulating current states on the edge. All right, so the one last thing is you fine-tune the material composition a little bit so that you move the Fermi level right inside this gap. So the bulk really becomes insulating, the surface is insulating, you only have chiral edge states to host this. All right. Okay, so if you take a closer look at these chiral edge states, these are topologically protected. They only live on the edge. What that means is, let's say if you have a film, right? If you accidentally drop it away from the floor, you knock off one corner, the edge states doesn't go away, right? You just it just circle around the entire geometry of this thing. Now, what if you have some defects? It goes around it, right? So this is a very robust edge states. It's more robust than the quantum spin Hall we saw earlier. So guided by these theoretical discoveries in around 2013 or 14, people finally realized this beautiful effect. We use molecular beam epitaxy to grow these thin films on gallium arsenide substrates. You can see this is beautiful layer by layer structures of the chromium, bismuth antimony telluride samples. And we can, at that time, we can already do a centimeter size wafer. This is a gallium arsenide 111 substrate. You can see we can achieve this macroscopic quantum anomalous states, okay? So this is what the transports look like, okay? So just for the disclaimer, everything I show here is at low temperature. In this specific case, we're measuring things at 20 millikelvin, okay? The blue curve is the RXY, right? You just see this beautiful perpendicular magnetic anisotropy under the out of plane magnetic field. Okay, so if you carefully look at the saturation of this resistance, it's actually saturated at the h/e square. That's the quantized states. Okay, now, yes. If you look at the RXX, the longitudinal resistance, okay, here it's sitting exactly at 0. That's the dissipation-less edge states we're looking for, right? Okay, more significantly, if you look at zero field, right? That's a zero field, zero resistance that we are all anticipated. Okay. All right, so this is a beautiful experiment. I personally really appreciate the beauty of this system. Since then, a few groups in the world has been able to reproduce this system, and we all see the consistently the same thing. Now, fast forward five years later, it turns out this behavior also can be observed in a little bit more fancy systems like the twisted layer bilayer graphing by a Stanford group. Also, there's intrinsic magnetic topological insulators. So you don't need to add external dopants. Manganese bismuth telluride itself gives you this quantum anomalous states. Okay. And things went on further. Last couple years, we even observed this fractional quantum anomalous Hall effect. So this is way beyond the wildest imagination. People at this point still don't understand why it's not fully understood why we see this fractional quantum anomalous Hall effect. What we know for sure is it's completely different mechanism from the classical fractional quantum Hall effect, because if you look at the fractional quantum Hall effect, you cannot have this 1/2 Feeling states. Okay, so fractional quantum Hall, fractional quantum Hall always happens at this odd denominator states, but here you can actually achieve a 1/2 Feeling states. All right, so what we did, we took a little bit further to create this tri-layer magnetic insulators. Okay, so I remember I told you we can add magnetic dopants into topological insulators, right, with MBE. Now, the advantage with MBE is you can add these dopants layer by layer. So what that does is you can actually create different mechanisms on the top and bottom surface. Okay, so it's very easy for MBE. We just turn on and off the shutters, right? So in this case, we use chromium on the bottom layers, and then we use a harder magnetic material, vanadium, and on the top layer. So effectively, we can control the coercivity of this top and bottom magnetism. Okay. All right. So here's one example, right? You have the magnetism hysteresis loop from the bottom layer of chromium, and you also have a top layer of vanadium hysteresis loop, right? So let's say these two layers are decoupled. So what happens when you scan the magnetic field? Let's start from this point, okay? So at a positive field, both of them are spins are polarized in the upward direction. Okay, so that is the same as a quantum anomalous Hall states we just saw. So you will see that the RxY, or in this case we plotted into the conductivity tensor. The RxY is quantized as 1, and the sigma XX is 0, right? That's your quantum anomalous Hall states, right? So the quantized E squared over H actually comes from the sum of the bottom and top surfaces, which each contributes 1/2 of the quantization value. Now, if we scan the magnetic field right here, we park it between the coercivity between the vanadium and chromium, you can actually put the system in this anti-parallel configurations. What this does is, well, each two surface still gives you 1/2 of E squared over H, but they are in the different directions. So they actually cancels out with each other. Okay, so this is actually relates to a very exotic states, which is called axion insulator. And I have a very brief introduction to this in the next slide. But for now, we just keep scanning the magnetic field this way, right? You can imagine if you keep going this direction, both of them will be pinned downwards. And you enter this quantum Nahm's states again, and then you go up this way. The chromium will flip first, and then you enter the axion insulator states again. All right. So that's pretty cool, right? But the result seems quite straightforward, right? So it turns out that middle state where you have this anti-parallel states is something very significant. Okay, these are called axion insulator states, and the name actually came from this detergent brand, right? So one of the theorists in the 70s, he's working on the dark matter, is looking for these elementary particles. There was some strong CP problem that in the elementary particle physics that people cannot solve. And then he just came up with the idea, what if there's some hypothetical elements introduced into this electrodynamic equations? Basically, we can clean up all these problems. So that's why he was in the doing grocery. He saw that axion detergent on the shelf. Hey, let's call this axion because it cleans up all these mess in the high energy physics. Okay. And then condensed matter, people borrow these concepts from the high energy. All right, we use axion insulator because this high energy dark matter systems particles actually is described by the same electrodynamic properties equations as our low energy axion insulators, right? So if you look at all these condensed matter people, we borrow a lot of things from high energy physics, right? Dirac states, Majorana particles, these are all originated from the high energy physics, but we can find a low energy copy of this in the condensed matter system. Okay, so when you have this intermediate state with all the anti-parallel magnetism, the axion insulator states actually it is described by this topological magnetoelectric effect, which we borrow from the high energy physics. All right, now, so far, everything we've done is with the perpendicular magnetic field, right? So what about we use some in-plane magnetic field? All right, so in this case, we still take the same material. We first initialize it with a perpendicular magnetic field, which drives the system into a quantum anomalous states again. Now, we remove the out-of-plane field, right? The system has PMA, so it stays in this configuration. And we start to apply in-plane magnetic field, right? So you can sort of imagine what will happen, right? One layer will rotate first, and then the softer layer will rotate first, and then harder layer will just follow, right? So that's exactly what we did, right? So we remove the perpendicular field, increase the in-plane field in this case. Okay, so we start from here. If you look at the Rxy or sigma xy, starts from 1. That's your quantum anomalous states because it has a PMA. It takes a little bit in-plane field to rotate it into in-plane direction. Okay, now move on to this intermediate state. Now, the softer chromium layer will be pulled into in-plane configurations. So what that gives you is now the chromium layer doesn't contribute any Hall signal anymore. So you only have a half-quantized top surface that gives you about 1/2 of the sigma xy. Okay, so this is a half-quantized Hall plateau. Even though I call it a plateau, you can see it's not a very flat surface. We still have some material improvements that needs to be optimized, but you can see if you take a derivative of this curve, it sits right here about 1/2 of the quantization, right? And then if you keep pulling the magnetic field into in-plane directions, even the harder vanadium layer would also rotate into in-plane direction. In that case, you have 0 longitudinal, sigma xy. Okay. All right. So again, that's a nice experiment. You can try different configurations. You can initial this thing at up or down directions. You can try to drive it into different in-plane directions. Basically, this shows you that this half quantization plateau always exists. Right, so it's neat. It's a demonstration, but what significance come out of this, right? So it turns out, again, it relates to something with the particle physics, right? So if you look at the band on the surface states, with the quantum anomalous states, we mentioned that the magnetism will gap out the surface Dirac states, right? So you have a little exchange gap here. Now, when you rotate the magnetic field, the chromium layer first becomes in plane, right? Now this will close this exchange gap on the bottom layer. So you have a Dirac cone on the bottom, a massive Dirac gap or gap Dirac states on the top. Okay, and then if you keep increasing the in-plane field, both layer becomes in plane. Now you have 2 Dirac cones, right? So this basically recovers to a classical Dirac topological state. Now this is a very unique situation in the middle right here, right? So if you take any Dirac materials, the Dirac cone, the Dirac points always comes in pairs. You cannot create single a Dirac cone, right? So we're all magnet people. So it's one analogy is if you take a bar magnet, you always have a south pole, north pole, right? If you break it, you still have a new pair of the magnetic poles, right? You cannot create this monopole. So in this case, it's almost like a monopole living in the momentum space. So we call it parity anomaly. So how this single Dirac cone is created is still a lot of things theoretically still people don't understand it. But this half quantized Hall conductance really points to the evidence of achieving this parity anomaly. All right, so this is not full enough plateau yet. If you look at the data I just showed you here, you see a little bit wiggly, roughly at 1/2, right, of the quantization, but it's not fully developed yet. I said this is because the material quality is not good enough, but also because this is in a very thin 2D thin films, right? You have 2 layers of magnets next to each other. They will couple, right? They will have some exchange interactions. So one example is if we increase the spacer layer thickness, you can see a better and better developed plateaus in the shoulder here. Okay. So I'll probably just skip this. Now, so this is pretty cool, right? So everything I showed you so far is on the longitudinal resistance, but sorry, on the transverse resistance, but we never look at the longitudinal resistance. So what happens to the longitudinal RxX? Okay, so here's the original data, right? So in this red curve here, that's your RxY we just discussed. You have this little wiggle at about half of the quantization value, about 12 kilo ohms. Okay, how about the longitudinal resistance? It goes up, eventually saturates at some number, right? So 52 kilo ohms, right? So does that ring the bell? Right, so if you look at the the aspect ratio of the channel is 2, right? If you convert it either into a conductivity or resistivity, this is not a random number. It's actually exactly at E squared over H. So in this in-plane configuration, the longitudinal resistance actually is quantized. This, well, the 1/2 plateau is something that we sort of expected when we do this experiment. We're just looking for that. But this is completely out of expectations. We don't know where that comes from. Okay, but we just want to make sure it's just this not just some random lucky scenario. Somehow this thing saturates at this number. So we tried samples with different geometries, this different aspect ratio. They always settle at this value. We even made this ring structures, right? So these are called Corbino structures. So the current is flying in the radial directions. There will be no edge states, okay? So the current goes from the inner contact to the outer contact. Everything is this direction. There will be no tangential current. So if you convert this thing to the sigma, again, you'll see that it saturates at E squared over H, right? So that's tells us this quantization happens in the bulk, not on the edge states, because in this Corbino disk structure, there was no edge states. All right, so now what we did next is we put on the gate. We want to make sure this is not some coincidence, the resistance value happens to be there, right? So we put a top gate on this device so you can modulate the Fermi level up and down. And then you do that under different in-plane magnetic field, okay? So the bottom curve is you have 0 magnetic field. Both layers are out of plane. You have these quantum anomalous states, and you have this 0 RXX, right? So that's your quantum anomalous states, what we expected. But as you climb up to higher in-plane field, you pull this spin into in-plane directions. Somehow, this in-plane quantization happens, and it just does not just cross this quantization value. It's actually parked at this number around for a certain voltage range. Okay, so this tells us it's not a random number. It's a very reliable behavior, and we saw that in multiple samples. Okay, so we call this in-plane quantization states. If you look at literatures, there are not much examples of in-plane quantization, right? So we know there's we know there's a quantum Hall, quantum anomalous. Every so-called Hall, quantum Hall states, they always happens in the Hall direction. The only time you see a longitudinal resistance quantization is in, let's say, quantum point contacts, right? So these are like nanowires, or even in some quantum spin Hall states, right? You have limited modes of the electron states in the restricted region. All these quantized longitudinal resistance happens in the resistance, meaning that it's independent of the aspect ratio. But in our case, it actually happens in the conductivity, or you have to normalize it with your geometries. So this is a very special case, right? So at this point, we don't know much about why this in-plane quantization happens, right? We have some initial guess because there are some defects in this magnetic topological insulators. If you look at the Dirac cones, there will be a lot of up and downs, right? If you cut this Fermi level inside, there will be some electron and hole puddles created, right? So at some location will be p-type, some location will be n-type, and these correlated electron and hole puddles performs a screening effect to avoid further disorder. So the resistance actually saturates at a quantized value. Okay, so this is just our interpretations. Still, we are at this point still not fully understood these results. All right, so enough about physics. We're looking at what can we do with this quantum anomalous states, right? So next couple slides, I'll quickly go through some of the applications of these things. All right, so remember, these are beautiful quantum resistance at 25.812 kilo ohms, right? So if you ask, what is 1 ohm? Right, you can say it's 1 volt divided by 1 amp, right? So, but in the SI unit, NIST is actually looking at how we can define this 1 ohm. Okay, if you heard about the quantum Hall states, the Nobel Prize laureate I just showed, von Clichin, he first discovered that the quantum Hall states can be used to define the unit of ohm, right? Because it's always h over e squared. So we know these two are just fundamental physical constants. So NIST for a while they used the quantum Hall to determine what is a standard unit of ohm, right? But that quantum Hall requires a high magnetic field, right? So high magnetic field interference with all these electronics, right? Also, if you want to measure current and voltage very carefully at low temperature, people use all these Josephson junctions, all these superconducting components to read off and compare currents. Okay, so all these things, superconducting things, they don't like magnetic fields, right? So NIST came to us. Can we have some of these magnetic topological insulators? We want to recalibrate 1 ohm. Okay, so we're very proud that they took our samples and now they use our samples to define the resistance, right? So in this case, we can achieve accuracy of part per billion. Okay, so that's 1 to the 9th accuracy of the resistance. Okay, so that's one fun application for quantum metrology, right? So another case we actually use it is for some RF applications. Okay, so the story is that if you look at so-called quantum computers nowadays, for instance, I use this IBM image. Their qubit chips really sitting down here, right? So it's a tiny, well, not so tiny, but still acceptable size. So when we talk about the scaling challenges for qubits, you can see all these challenges. It's not much of the qubit itself, but all these peripheral electronics, these RF cables, and especially at the bottom part, this is where you have most limited cooling powers and space, right? So you want to minimize the footprint of these RF components. Okay, so how do we do that? Right, so one important element, you see most of the things down here, these are circulators, RF circulators, right? So they regulate the directions of microwave signals. We want to avoid these two-way country roads of the quantum information process flow. We want to divide these, right, incoming and outcoming traffic. So a natural way to do that is to use this magnetic topological insulator. Okay, so we built this magnetic topological insulator circulators. You send in all these RF signals capacitively coupled to your quantum anomalous disk, which is this little ring in the middle. And because we have these edge modes, all these signals are propagating on the edge in the form of edge magnetoplasmas. Okay, so these are like slow waves. They have a much shorter wavelength. So with that, we can actually achieve pretty good isolation, which is about 20 dB at low temperature. Okay, If you look at the working frequencies of these devices, we can, depending on the size of the disk in the middle, we can actually push a few gigahertz. So that's where all the qubits are operated. Usually qubits are at a few 5 to 7 gigahertz frequencies. So and the advantage of these things is that because of the magnetoplasma states, we can miniaturize the circulators by roughly 2 to 3 orders in terms of the size. So that will really save us all this footprint at the bottom of the dilution fridge. Okay. All right. So just last couple slides, I want to talk about the very broadly what I'm doing right now at the Minnesota. So I am very interested in low temperature. Okay, we have a cryogenic system in my lab, and my personal belief is in the future, well, we know all these data centers are consuming tons of electricity, right? So what if we, people have been talking about immersion cooling, all these cooling technologies. What if we go extreme and cool things down really hard and down to temperatures? How much gain of the energy saving can we gain in this case? We can replace all these interconnect wires with superconducting materials. We can run a lot of devices on superconducting principles. Basically, we have to redesign everything, every circuit elements. But hope is using all these quantum materials, the gain of the energy saving in the device parts can outweigh the overhead cost of cooling. Okay, so if you have a let's say I use MRAM for example, if you just run things at room temperature, keep building things, the optimistic prediction, the things will just go, the cost will just go up linearly, right? So, but for superconducting things, let's say you use superconducting materials to drive magnetic memories, you have some upfront costs in building infrastructures, putting all these cryogenic systems into your data center, but the circuit energy of operation will be so low that eventually at some inflection point you will see benefits. Okay, so for us, we are on the material and device side of things. We're looking at how to actually design these superconducting spintronics. The other thing I work on, this is my most of my PhD work. We look at the chiral materials. We saw this. I work on the single element tellurium, which is a simple and beautiful chiral materials. This is one of the hot topic in the research nowadays. There is something called chirality-induced spin selectivity. When you pass the current through these chiral materials, they're not magnetic, but intuitively thinking, if you have this little orbits, the electrons hop through this little springs or coils, it will pick up some spin. Okay, the spin will actually be polarized by just passing through this non-magnetic chiral materials. Okay, so if you think about the applications, we can generate spin currents without any magnets. Okay, we can also control all these spin states with all electrical signals. So right now we're looking at the single element tellurium. We can controllably grow the left-handed, right-handed chiralities. We're studying all these spin related chirality-induced spin selectivity related transport behaviors. All right, so just to summarize, I worked on this MTI for quite a while now. There are a lot of fun physics. There's some new applications. We're in terms of real applications, we're looking at things like maybe 5-10 years later. But as a fun project, I really enjoy doing all these new physics. Most of the work done was done at the UCLA with my postdoc advisor Ken Wan and the PhD student team. We also collaborate with Lawrence Livermore National Lab on the RF measurements. And also we use the fundings from NSF and DARPA. And also I want to give thanks to the very dedicated staff at the National High Magnetic Field Laboratory who support a lot of these experiments. Okay, so with that.
Well, let's thank our speaker. We have time for a couple of questions. We'll kind of go through the room here first, and then we'll go online because usually there are little audio switchovers. Any quick questions in the room here?
So one question about the in-plane field that you have. So maybe slide 20 around. So you have this plot versus like we have positive and negative direction.
Oh yeah,
in-plane.
Yeah, right.
So is there any way to break that symmetry for the positive and negative in-plane fields? Different type of resistance.
So that's a good question. We haven't tried that. If you ask me, my intuition is maybe we can play with the lattice structures a little bit. Now the material itself has the threefold symmetry instead of twofold. Maybe there's something we can do with that. But for now, we only try this two directions. Yeah.
Quick follow-on question. So low temperatures seem to be critical in order to get this effective. Magnetic field strength, it looks like you need at least about a Tesla or so. Is that true?
So in terms two questions, right? One is the temperature restriction, one is the magnetic field restriction, right? So let me answer the magnetic restrictions first. We tried a very simple way. For instance, vanadium, they are easy to magnetize. We basically put a small, a permanent magnet to our sample. That's enough. Like a few oysters is enough to magnetize it, just like a hammer, right? We cool down with the field. In that case, only a few OE is enough to fully magnetize it. Well, you could call it heat-assisted quantum anomalous states.
Lack of heat-assisted. Yeah.
Yeah. The other question is the temperature requirements, right? Right now, the record is maybe 2 Kelvin or 4 Kelvin to reach a very good quantization. But that being said, there's no fundamental limit why this only happens at low temperature. In fact, the first theoretical prediction says we can do that at 30 Kelvin. Our group tried, but for some time we didn't see that, so we just gave up. And then another group in China actually put this thing at the 20 millikelvin. They saw it first. So the theory is right on the big picture, but they didn't tell us these details. Now, the problem in that case is this, at the end of the day, it's material quality, right? So we have all these Dirac cones, right? So this energy gap, if you do ARPAs to look at this local gap, it is indeed around on the order of tens of Kelvin. But you have this dislocations everywhere. This causes a little bit of fluctuation in the energy scale. So that creates an effective gap, which is a couple orders smaller than that. Meaning that if you create very clean, perfect materials, right, industry standard materials, maybe we can push this thing to 30 Kelvin. And people, a lot of theorists now start to search the entire material database and see, oh, there are some materials potentially can be used for room temperature applications as well. It's just that we don't know how to access these materials. Yeah.
Sounds very exciting. Time for one last question online, if we've got it. If not, then we'll thank our speaker and continue the discussions offline here. Thank you.
Yeah.
Thank you, everybody. Stop recording and we'll end the meeting.